In lesson 7.6, solving exponential and logarithmic equations, there are going to be 4 different types of equations that we need to know about. So we're going to start with the ones that deal with exponents. So here I have the property of equality of an exponential equation states that if our bases are the same, so here we have base b, and it equals base b raised to the power of x equals base b raised to the power of y, then it makes sense that x must equal y. Here we have an exponent on one side. So we're going to use a logarithm so we don't have a variable as an exponent. So we can rewrite this as 4 is our base, so log base 4 of 11 equals x. And then you remember only base 10 technically can be done on the calculator, but we can rewrite it using our change of base formula and then put it into our calculator to get a value. So when we use our change of base formula, recall that the 11 goes in the numerator, the base value goes in the denominator, and it should come out to equal approximately 1.729. And we can check this by putting this value back into the original equation. So if we raise 4 to the power of 1.729, it equals approximately 10.989. So not quite 11, but remember we rounded here, so this answer is going to be off just a little bit. One last thing I'd like to point out with this problem. So remember we put our base, then the 11 came across, and then our exponent went over here. We would have gotten the same equation, the same red equation, had I said multiply this side by log 4, and then if I do that to one side, I do it to the other, and we would have multiplied this side by log 4, and the log 4 and the 4 would have canceled, so we would have gotten x equals log base 4 of 11. So we would have gotten the same exact problem. So exponent on two sides, but before we actually do that, let's look at a simpler problem. So we're trying to get 13 raised to the power of 9x plus 5 equal to 1, and we know that anything raised to the 0 power would be equal to 1. So we need to make 9x plus 5 equal to 0. So what we're going to do is to take that expression, 9x plus 5, set it equal to 0, subtract 5 from both sides, 9x equals negative 5, divide both sides by 9, so x equals negative 5/9. So we know in order to get the left-hand side equal to 1, the x has to be equal to negative 5/9. And we did that by just working with the exponential expression. With this one, we have exponents on two sides. So if you remember from our property of equality for exponential equations, we said if we can work with these if the bases are the same. So somehow we have to get the 3 to match the 1/9, or the 1/9 to match the 3. So we know that 3 to the negative 2 is the same as 1/9. So that's what we're going to change that value to. All right, so remember if we had 3 to the negative 2, we know that that means that the 3 goes to the denominator, so 1 over 3 squared is equal to 1/9. So that's how that works. Now we have a power raised to a power, so we're going to have to multiply negative 2 times x, and then the negative 2 times the 3. So again, we distributed the negative 2 to the x and the negative 2 to the 3. Now we have the same base, so we can focus on just working with the exponents. So I'm going to bring down my x, bring down my negative 2x minus 6, and then we're going to work to isolate the x. Okay, so we added 2x to both sides, then divided both sides by 3, so x equals negative 2, but we want to check to make sure that that works. So we're going to insert it back into the original problem. So 3 to the negative 2 equals 1/9. Negative 2 plus 3. 3 to the negative 2 equals 1/9. And then negative 2 plus 3 is 1. So 1/9 to the first power is the same as 1/9. So negative 2 works. Here we have a log, or you could have a natural log on one side, and on the right hand side I have the property, which is very similar to our exponential equation property. So the first thing we need to do is to change this to an exponent, because the x is part of the logarithm. So we're going to rewrite it. We're going to take our base 2, and then the 5 comes over. That's our exponent, equals x minus 6. So 2 times 2 times 2 times 2 times 2 is 32, equals x minus 6. We add 6 to both sides, so x equals 38. All right, I have one more for you to try. And we can use calculators for these, but sometimes just doing it by hand is easier. And I'll show you calculator problems in class when we meet. So go ahead and pause the video and try the next problem. So we have our base 7, then our exponent 2, the 3x minus 2 goes on the opposite side of the equal sign, and now you just have to work to isolate the variables. So we're going to go ahead and first say 49 equals 3x minus 2, add 2 to both sides, 51 equals 3x, and divide both sides by 3, so x is equal to 17. All right, so remind me to show you how to use the calculator on some of these, and then we just have one more slide. All right, so in this problem, both sides are log base 4, so we're just going to get rid of that, and we're going to look at the expression 2x plus 8 equals 6x plus 2, and then just work to isolate the variable. So we'll subtract 2x from both sides. So 8 equals 4x plus 2. Oops, I'm going to have to stop myself for a minute. I misread my handwriting. This isn't a plus 2. It's supposed to be a minus 12. So I need to change these. So this is a minus 12, minus 12. So now we're going to add 12 to both sides. So 20 equals 4x. Divide both sides by 4. So x equals 5. And if you sub the 5 back in, you should see that it works. For this problem, we have our logs on the same side of the equal sign. We could use our change of base formula and put it into the calculator, but again, we'll take a look at that in class. Because we have the same bases, we can multiply like we did in lesson 7.5, so we're actually condensing the problem. Okay, so we knew it was multiplication because we had the addition sign here. We're going to go ahead and distribute the 3x, so we end up with log base 6 of 3x squared minus 12x equals 2. So at this point, we're going to go ahead and write it with exponents. So because it's base 6, we have 6 squared, and the square comes from the 2 over on the right-hand side, equals 3x squared minus 12x. Now, if you remember, when we were working with quadratics, it looks like this is going to be factorable. All right, so 6 times 6 gave me the 36. Then I moved all the values to one side of the equal sign. Then remember, we ask ourselves, is there anything we can factor out? And we notice that 3 is a common factor for all three terms. So we end up with 3x squared minus 4x minus 12 equals 0. Then we have our 3 out here on the outside. We know the first term has to be x, what multiplies to negative 12 and adds to negative 4. So that's going to be a minus 6 and a plus 2. Then we're going to set the x minus 6. Remember how we do that? We set it equal to 0, add 6 to both sides. So we know 6 is equal to, or excuse me, x is equal to 6. And if I said x plus 2 equals 0, x is going to be equal to negative 2. So it could be one of these values, or maybe neither value works. So we're going to sub it back in to see if they work. So remember, when we're working with logarithms, there's a domain restriction, and it says that x needs to be greater than 0. So we know that x equals negative 2 can't work. So now we're going to sub in the 6. All right, so I subbed in a 6 everywhere there was an x in the original equation. 3 times 6 is 18. 6 minus 4 gave me 2. We have this addition sign, so we can condense it, and we know that when there's addition, it really means that it's multiplication. 18 times 2 is 36. Now we're just going to write it using exponents. So we take our base 6, the power is going to be 2, and then the 36 goes on the other side of the equal sign. So 36 equals 36 works, so x equals 6 is a true answer.